All right, so we are going to start integration by substitution, a really important topic at the end of our Calc 1 course here, and one that you want to get down as well as you can before you take Calc 2. It's really important in Calc 2 to have a solid understanding of integration by substitution, because in Calc 2 you're going to learn a lot of other techniques, so you really want to have this one down. And this is the one you'll always look for first to see if you can do this first. What it's going to be, so first of all, let's just kind of remember, when we integrate or take antiderivatives, there's no product rule, there's no quotient rule, and there won't ever be. This is going to be, this semester, this is our only hope if we have some products, some quotients, and compositions in particular, because the closest thing we can relate this to with differential calculus is like running the chain rule backwards. It's kind of the closest thing that we can relate this to. So it's going to be used anytime you can't just do like some basic algebra, or you can't just do like a basic trig identity and kind of get it into a form that you can integrate. If you can't, then for us, this is going to be our only hope, is integration by substitution. So let's kind of take a look at the steps in this opening example. First, maybe let's just quickly mention these two integrals at the top. Like, notice that even if you multiplied out 6x minus 5 to the fourth, so even if you were to multiply that all out, you're still taking 6 divided by that, and so you couldn't break it up into different terms. Same thing with the second one with that radical. You can't split a radical with adding and subtracting. So lots of things like that are going to be situations where we can't just do some algebra and get it into a form where we can integrate it. So let's take a look at this little example off to the side and kind of talk through these steps. I'm going to slightly change this example because you might look at it and say 3x minus 4 squared, no problem. I'll just multiply that out and, binomial squared, no problem, easy. But let's just change this to sort of take that option out, or certainly make it a lot less feasible. Suppose this was to the 12th power. Yeah, now all of a sudden multiplying a binomial to the 12th doesn't seem like such a fun thing to do. And obviously we started off by saying there'll be lots of times, like these ones at the top, where there is no such algebra you can do. All right. So your first step is going to be to identify and look for something that looks like an inside function. So think about compositions of functions and what is an inner function. Think about how when you've learned chain rule, every time that we would say, oh, then times the derivative of the inside, those insides, that's what you want to pick for a U. And as we first start, a lot of your intuition will be correct. So when we look at this function right here, I have this 3x minus 4 that is inside of a binomial being raised to the 12th power. So it's inside of this 12th power function. So that would be my choice for U. So you're always going to start off by letting U equal what looks like an inside function. After that, that's kind of the only thing you have a choice in the matter over. The rest of it, we have to hope that the calculus and the math works out. So the next part is, now we're going to take the differential of that U. So we're going to take du. Now, one thing I want you to remember when I say the differential, yeah, you're kind of just taking the derivative, but we talked about differentials before. Remember, we had, like, if I said in a previous section, suppose I had, x cubed minus 3x squared or something, and I said take the differential, that differential was that dy equals, and then we sometimes even called it like the differential form of the derivative. So dy was equal to that derivative dx. And we, of course, had a lot of application problems, and we talked about the specific meaning of the dy as the change in y on the tangent line, and how that's a good approximation for the actual change in y, and so on. But this is what I'm talking about in this second step. So we're going from this u into the du, and instead of saying, oh, du dx equals 3, we're saying du equals 3 dx. So we are going to be taking then this differential form, if you want to call it that, of the derivative. So du equals 3 dx. And that, just so happens on this first one, matches up exactly with what is left in that integrand. That will not always be the case, and we'll slowly work ourselves into lots of situations when it's not a perfect match. But initially, we got a perfect match. All right, now we are going to make our substitution, step 3, for u and du. And what we need is for the entire integral to be out of u's and du's and out of x's and dx's and into u's and du's. So on this one, as we notice, we would say, okay, that 3x minus 4, that is now being replaced with my u, and the 3 and the dx together were replaced by the du. All right, that is now something that we can integrate. The one thing I want to change is we actually have our u to the 12th power. All right, that is something we can now integrate. So the antiderivative, or the integral of u to the 12th du, so integrating a function of u with respect to u, is now our power rule. So here's our u to the, in this case, the 13th power divided by 13 plus c. And then your last step is going to be to go back in and replace that u with what it was originally. So u here was that 3x minus 4. So you want to, in your very last step, you're going to replace u with what it was equal to originally. So again, in this case, we end up with, u to the 13th over the 13th power. Over the 13, sorry, u to the 13th power over 13. All right, so this is what we would have ended up with. There's a couple of things in here. First of all, when we got to that point that we had the integral of u to the 12th du, it is crucial that we recognize that there can't be any x's at that point. It would not have made sense to say the integral of x to the 12th du, for example. It all has to be in terms of u's and du's. And then just kind of one other thing, when we're done, we can always do a little check if we want to see if we get back to the original function. So if I take the derivative with respect to x of that final result that we had there, so if I take the derivative with respect to x of this 1/13th 3x minus 4 to the 13th power, of course plus c, but derivative of c is going to go to 0. So if I take this derivative, chain rule says we would bring down the 13, that would reduce with the 1/13ths, and then we'd have the 3x minus 4 to the 12th power, and then times the derivative of the inside, so times that 3. And so what we ended up with is 3 quantity 3x minus 4 to the 12th. So if we want to, we are always able to run a little check when we're done and make sure that we get what was in that original integral. And we do. All right, so let's look at some more examples here. So let's start with number 1. Gosh darn it. Number 1. Suppose we have the integral of 3x squared over the quantity of x to the 3rd plus 9 raised to the 4th power dx. Now, the first thing I want you to, I just want to make a comment here that, we're going to be throwing around a lot of dx's and du's, and sometimes students have a tendency to drop them, and you can't. They're important. When we talk about these integral problems, I want you to think of the integral symbol here, this indefinite integral that's telling you to take the antiderivative essentially, and the dx. Kind of think of those as bookends on your problem. And whatever is in between those bookends, that's what you're supposed to be taking the antiderivative of with respect to whatever this variable is. It's really analogous to, like up here when I did this little check and I used this differential operator, that little d right there, that is telling you, I didn't mean to fill it in that much. That little d is telling you to take the derivative, and then the over dx part is saying with respect to x. But they go together. You don't just have the d, you have the d over dx. And that's the same thing we have here, though we kind of break them apart. We have the integral and then the dx as kind of bookends on what we have here. All right, so first of all, even if we could multiply out or wanted to multiply out that binomial to the fourth, that's no good because we'd have a monomial divided by a polynomial, and we cannot get that into separate terms that we could integrate by hand. So our only hope is going to be some sort of a U-substitution. So we want to start by identifying what looks like an inside function. And many times, especially initially, your instinct is going to be correct. Not always as we go through and we add some complexity, but initially I think about, kind of like my opening example up there, what looks like something inside of another function. And what we see here is right here, this x cubed plus 9 is being raised to the fourth power. So this looks like my choice of an inside function pretty intuitively. U is equal to that x cubed plus 9. So that's the only thing I have really control over in terms of my choice. Now you don't pick du, you take the differential. And so we just see what we get. So du is equal to 3x squared dx. And yes, you need the dx. This is the differential or the differential form of the derivative. Now, just like the first one, for our first example we're doing here from scratch, this is a perfect scenario. 3x squared dx just so happens to be exactly what I have left in that original integral. So as we look at what we have here, this is going to be absolutely perfect. We are going to have the integral of, now being careful that u is to the fourth power, but it is in the denominator. So we want to be a little bit careful, make sure you're keeping that down in your denominator. And then it's kind of up to you with this du. You will see it written a couple ways. So sometimes if there's nothing else left in the numerator, you will see it from time to time where they just write it in the numerator. I think initially for students it might be easier to see that as the integral of 1 over u to the fourth du, especially if you're kind of thinking along the lines of what I was just saying with thinking of this as like being bookends on the problem, so to speak. So either way, this is what we have. So we can see exactly what got replaced in yellow for the u, and what's in green, that entire quantity became my du. So now we have this in a form that we can actually take the antiderivative of this. So we know how to integrate u to the negative fourth. We do need to do that first, du. And this is going to be a power rule. So we're going to add 1 and divide by it. So u to the negative third divided by negative 3 plus c. And if you want to maybe write that as negative 1/3. And then the last step is going to be replacing u with what it was originally. And that's the x cubed plus 9. Now again, that is my last step. You cannot do that before this. Sometimes students will go through all this work of getting things in terms of u, and then like way back here, they're putting it back in with the x cubed plus 9. Well, no, if I knew how to integrate 1 over x cubed plus 9 to the fourth, then I wouldn't need all this U-substitution, right? So that final resubbing doesn't happen until the very last step. And again, especially on some of these first examples, let's run the check. I'm not going to always show our checks, but let's go ahead and do that here. So let's go ahead and just check it out. So if I'm taking my derivative here, I'm just going to jump right in and take the derivative. So I'm going to bring down my -3, and then I'm going to have my x cubed plus 9 to the -3 minus 1. I'm taking my derivative here, would be -4. And then chain rule times the 3x squared. So obviously the -1/3 and the -3 reduce. And so what I have here is exactly equal to my original integrand. It's that 3x squared over x cubed plus 9 to the 4th. So it checks. So again, I won't always show the checks, but it's kind of nice to do it initially a little bit here, I think. All right, so a nice kind of perfect substitution there to start that one. Okay, let's look at another example. So number 2. So let's take a look at, oops, didn't mean to do that. All right, so number 2, let's do the integral of the square root of 4x minus 1 dx. All right, well, kind of no matter what, we always have to rewrite these square roots as exponents. So let's go ahead and do that. So 1/2 power. Hey, but again, I can't split a radical. This does not become like 2x to the 1/2 minus 1 or something. You can't split a radical if there's adding and subtracting. So no options here. The only thing I know how to take the antiderivative of would be just plain old x to the 1/2. And that is not what I have. So my only hope is a U-substitution. So again, we want to look for, and we have a similar type of inside function here, right? Something inside of an outer power. And so that's going to be our choice here for our U. So U is going to equal 4x minus 1. Now we take the differential form of that derivative, so du equals 4 dx. Well, this one's a little different here because I don't have a perfect matchup, right? I'm liking the looks of what I'm seeing here with my u to the 1/2. That looks like something I'm going to be able to make a go of. But I can't just neglect this dx part. I have to get all of the x's and dx's into u's and du's. So it would make absolutely no sense here. This is mathematical nonsense to say u to the 1/2 dx. That makes no sense. So we can't have that. So we have to get the dx in terms of u's and du's. So here, it's not a perfect match, but I think, if we were sitting in class having a discussion, it wouldn't take long for someone to say, well, why not just divide by the 4? So if the problem, sorry about that, if the problem here is this dx, if that is my problem, which it is, that I have to get rid of, well, that's what I can isolate for right there. There's the dx. So if I went ahead and just divided both sides here by this 4, I'm going to have my 1/4 du, or du over 4 if you prefer, equals dx. So this whole quantity now, I can replace my dx with this 1/4 du. So the dx can be replaced with the 1/4 du. Now for emphasis, I put in a couple little dots there. I just want you to be aware this is all multiplication. So kind of in the future, what you're probably going to see me do immediately, I wanted you to see kind of like the direct linear, yellow to yellow, green to green substitution. But in the future, what I will probably immediately do, since these are all multiplication of factors, is I will probably immediately factor out that 1/4 just as a constant multiple in front. So this is probably what you'll see me do more often as we move forward. All right, but this looks great. This is something that we can actually integrate. So we go through all this work. Don't forget to integrate. Sometimes I'll see students they get all their U-substitution. It's like they forget to integrate. So now we can integrate. So now we can take our power rule, so u to the 1 1/2 or u to the 3/2 divided by 3/2 plus c. But of course, I don't ever want you to leave things with complex fractions. So dividing by 3/2 is like multiplying by your 2/3. And then you can do a little reducing there. And then your final step, of course, is always to replace your u with what it was originally in terms of your original, in this case, x variable. So u was equal to 4x minus 1. So there's our final answer, 1/6, 4x minus 1 to the 3/2 plus c. Again, some of these early ones, it's probably nice to check it out and see what we get when we take the derivative. So you bring down the 3/2. Of course, you could do some reducing here. So, but then you'd have your 4x minus 1 to the 3/2 minus 1. So 3/2 minus 1 would be 1/2. And then by chain rule times the derivative of the inside. Well, guess what? This 4 is going to reduce with the 2 times 2 that's left in that denominator there. And so we just end up with our 4x minus 1 to the 1/2, or that's, of course, the square root. So it checks out. All right. So one of the things you may be feeling right now is that this just feels a little bit awkward. That's common. You may also be feeling like, as we are doing these problems, it's just a lot to keep track of because you're identifying your u, and then you're taking a derivative when you do the du, and then you go back to the integral where you're taking an antiderivative, and then at the end, sometimes you're going to be checking where you're taking a derivative. So you really have to be really mindful as you're going along of kind of what you're doing and why. All right, so let's look at maybe just a couple more in this video. So number 3, let's look at the integral of, and let's do 3 theta cosine of theta squared d theta. So as we first look at this one, it's all kinds of problems that prevent me from taking the antiderivative or integral directly. There's products, there's compositions, even without the 3 theta. If it was just cosine of theta squared, I can't do that. The only thing I could maybe do is just cosine of theta. That integral is sine theta. But we got all sorts of issues here, right? We got a composition, something inside of the cosine function. We have a product of 2. So U-substitution's our only hope. So the first thing is we want to pick a u. So here's a different kind of inside function, but I think one that is typically pretty clear to students, that what is inside of the trig function. So think about all those times when you had to apply chain rule with derivatives. That was applicable when what was inside of that trig function, was more than just like a plain x or a plain theta. So there's our inside function. So this is going to be my choice for u. So u is going to be our theta squared. So there's my choice for u. All right, that's the only thing I really have control over. I don't get to pick du. I have to take the differential to see what du is. So du here is 2 theta d theta. Well, maybe at first it's like, oh, bummer. I was hoping it would be 3 theta d theta because then it would be a perfect match. But that's okay because the key components are there that we need, which are the thetas and the d thetas. All right, so here's the thing. If it had been 3 theta d theta, that would have been great, but it wasn't. So first of all, this constant right here, this constant multiple of 3, we can always carry constant multiples along. So I'm even just going to pull that little guy right there out in front. So if it had been part of the du composition thing over there, the du, it wasn't. If it had been, great. If not, just forget about that. It just gets carried along. So then what's the problem with what we have left in the integral? What do I need to get rid of? Well, I need to get rid of the thetas and the d thetas. So what's left over that is not yet accounted for is going to be that theta d theta. Well, that's kind of nice because this is what I was saying. Constant multiples are never going to be an issue for us as long as the variable parts match up. So I need to get rid of theta d theta, and it just so happens I have theta d theta, and I can isolate for it down here by just dividing both sides by 2. So I have my 1/2 du is equal to my theta d theta. All right, so this is going to be my replacement for theta and the d theta. All right, so I am typically going to, any constant multiple, including like this 1/2, I'm just going to bring it out in front right away, and then I'm going to put the kind of du portion over here. So again, what are we doing here? We are replacing the theta d theta with the 1/2 du. I just want to put the 1/2 in front. These are all multiplications of factors, so I get to do that. All right, so what do I have else left? I have my cosine of, and of course I am replacing that u squared is being replaced, I'm sorry, theta squared is being replaced with u. So this looks good. This is something that I can take the integral of. I know that the antiderivative or the integral of cosine is sine of u plus c. And then my last step is to replace that u with what it was equal to originally, which was theta squared. And so that's my final results. And again, just kind of continuing here initially to do some checks. So when I take this derivative, 3/2 gets carried along. Derivative of sine of a function is cosine of that function times the derivative of the inside. And that's perfect. That's exactly my integrand that I started with. So I definitely did it right. All right, maybe just one more for today. All right, so last one, number 4 here. Suppose that we have the integral of 3 over 3 minus 5x dx. All right, well, I don't really see, like initially, quick glance, I don't see a super obvious inside function. I don't see something raised to a power, and I don't see certainly like the last one we did with the trig function. But my guess is, if we were in class, what I'd probably say, if no one had any ideas, is I might say, okay, well, how about if I rewrote, if I had given you this instead, 3 times the quantity, and I brought that entire denominator up, but then I'd have to raise it to the negative first power. Well, then all of a sudden, the inside part becomes a little more clear. Oh, yeah, that 3 minus 5x, I could think of that denominator really as an inside. So it's maybe not as obvious as the first couple, but yeah, that's an inside function. So let's start with that. Let's let u equal this 3 minus 5x. So that's my choice for my inside function. So many times, if you don't see maybe one of the more obvious inside functions, then maybe try, if it's a fraction, the entire denominator. All right, well now I am taking my du derivative, which is negative 5 dx. All right, so initially here, I'd like it if maybe in that original integral, if that numerator happened to have been a negative 5 rather than the 3, but it's not, so that's life. Constant multiples, I always want you to think about, are never an issue. So with this one, once again, it looks like I have, so this is going to be equal to, I have a constant multiple of 3 that's going to be carried along here in front. So I like to just kind of bring my constant multiples out in front. So 3 times the integral of, and now I'm going to have my 1 over, and that 3 minus 5x, That's definitely going to be my U. So there's my U replacement. So what's the problem? Well, the problem is, of course, what needs to be replaced are any lingering x's or dx's. Well, I have a lingering dx here. And so looking at my du equals negative 5 dx, I need to then isolate for just the dx. So we need to divide both sides here by that negative 5. So what I have is that negative 1/5 du is equal to dx. So that negative 1/5 du is going to be my substitution for the dx. All right, so again, what I like to do is I like to, anytime there's a constant multiple, I like to kind of just bring it out in front right away as a factor. So I'm going to bring the negative 1/5 portion just out in front with this 3. And then, of course, the du, I'm just going to put at the end of the integral. Or you could slide it up in that numerator. Du over u would be a really common way to see that. But this is one that hopefully we remember. It's not the power rule. If you did u to the negative first and then tried to integrate that, you'd have u to the 0 over 0 if you were thinking power rule. So that's always our little reminder. Oh yeah, that's the one that's the natural log of the absolute value of u plus the arbitrary constant. And so last step, let's just go ahead and replace that u with what it was originally, and then tack on our plus c. All right, so we're going to end with that one. When we come back next time, we're going to look at, there's lots of different scenarios that we're going to need to familiarize ourselves with, and so we'll pick up from here next time and look at some more examples.